we also need to identify how these parts and these activities of the parts or components are organized. And finally, and importantly, we need to understand or discover how it is that the coordinated activities of the parts or components of the mechanisms are producing the target phenomenon. And that should give us some kind of intuitive understanding of the causal structure of the system that is producing the phenomenon. So that's the goal. One notion that is particularly prominent in discussions of mechanistic explanation is that of constitutive relevance. So to provide an adequate mechanistic explanation of the target phenomenon, we need to have a way to discriminate between the factors in a mechanism that are relevant the factors that are relevant to a mechanism, to the mechanism producing a target phenomenon, and the factors of the system that are not relevant. That's essentially a boundary problem. We want to figure out which entities and activities of the target system are constitutively relevant to a phenomenon when there are parts of the mechanism responsible for the target phenomenon. And in order to solve this boundary problem, find out which components of the system are causally and constitutively relevant to a given mechanism that produces a given phenomenon or behavior. The classic approach is to turn to interventions. So really, that's the fundamental operation underlying causal explanation in the new mechanist framework. It's the intervention. So suppose that you have two variables, x and y. Then really the idea is that x is causally relevant to y if there's a typo here, and only if some intervention on x would make some difference for y. So flesh that out a little bit more. X is causally relevant to y if and only if there is some possible intervention on x. Doesn't have to be an actual intervention, but at least some possible intervention, such that if such an intervention were to occur, if we were to perform this intervention, if it can be performed, then the value of y, or at least some, the probability distribution of y, would change, right? So the idea is that it would make a difference for y. And this has been operationalized more specifically in the new mechanist framework in terms of manipulability of the components of the mechanism. So the idea is that there should be some intervention on a putative component of a mechanism that should change the target phenomenon produced by the mechanism, if that component is to be constitutively relevant to the mechanism. I think there is
Raphaël,
a question.
Yeah. So what if X is, some kind of post-Y filter? How do you tell that X is actually causally involved and not just changing your observation of Y?
Yeah, thanks. So I'll say a little bit more about that later when we talk about specific methods that are used in the context specifically of neural networks. But indeed, the idea is that you should have. I just finished the slide. So you for the component to be constitutively relevant, you should have potential for intervention on both ends. So some intervention on the component should change the target phenomenon. Some intervention on the phenomenon should also change the component's activity. Now, there's a very sprawling literature on that specific characterization of constitutive relevance. It includes, among other things, discussions of the sort of thing you mentioned. So how do we make sure that we're really identifying the components of the mechanism that are strictly relevant to the mechanism in question? I'm not going to get too deep into that now. I'll maybe first work through the specific case of neural networks, and maybe we can come back to that at the end if you still have that concern. Okay, so that's all well and good, but in practice, how do we do this? Well, that's very tricky when it comes to the kinds of complex systems that we might be interested in the context of this aspirational goal of providing mechanistic explanations in the life sciences and in computer science. So when it comes to explaining the behavior of these kind of complex systems, like the human brain or artificial neural networks, things get quite tricky. And they get tricky because we don't want to merely redescribe the behavior of the system as we've discussed. We don't even want to just predict the behavior of the system. We want to explain it. We want to explain it, and we want to explain it in a way that accounts for mechanisms. So at least in the case of artificial neural networks, as opposed to biological neural networks, we have access to the ground truth in terms of the model weights and the activations of the nodes or the units in the network in response to certain inputs. And so we could literally provide the full input-output function computed by the neural networks if we really wanted to. It wouldn't look very pretty, but we could do that. And that's why I mentioned early on that there's a trivial sense in which neural networks are not black boxes. But as I also mentioned, that wouldn't be very helpful as an explanation of a specific behavioral phenomenon. And so, for example, they wouldn't really tell us how convolutional neural networks recognizes dogs in an image, or how a language model resolved the reference of a pronoun in a sentence, for example. So what that tells us is that mechanistic explanations need to be pitched at an adequate level of abstraction. And just spelling out the full input-output function computed by a neural network is not the right level of abstraction. Even there is hardly any abstraction there. And so finding the right level of abstraction, or providing an explanation pitched at the suitable level, can be done by providing an abstract causal model of the target system, and more specifically, a suitably abstract causal model. I'll talk about this more in a second. And an abstract model of this kind is generally explanatory, to the extent that it actually reveals the causal structure of a mechanism, or at least aspects of the causal structure of a mechanism. So that's an important point. So people have been thinking a lot about how that should work in the context of cognitive neuroscience and systems neuroscience, and the kind of models that are put forward in those fields. And in that context, Craven and Kaplan have proposed an influential account of mechanistic explanation in terms of a set of mapping constraints. So that's what they call the model to mechanism mapping, or 3M constraint. So these mapping constraints are intended to distinguish between, on the one hand, merely predictive or merely descriptive models, models that merely provide some accurate description of the system or some prediction of the target phenomenon, and models that are genuinely explanatory, that provide genuine explanations. So here is how they frame their constraints. So in successful explanatory models, in cognitive neuroscience or systems neuroscience, first, the variables in the model correspond to components, activities, properties, and organizational features, of the target mechanism that produces the phenomenon. And secondly, the dependencies posited among these variables in the model correspond to the causal relations between the components of the target mechanism. So you need to have a mapping between the variables of the model and the components and activities of the mechanism. And you also need to have a mapping between the dependencies in the model, the edges, if you think of a causal graph, and the causal relations among the components of the target mechanism. So we want to find that kind of mapping. And that's very useful in the context of what I just discussed about the importance of causal abstraction when it comes to complex systems. Because again, if we want to hope to have an intelligible notion of mechanisms at work in a complex system such as a biological or artificial neural networks, we need to find a model that works at the right level of explanation. Or right level of abstraction, sorry. Okay, so that's a very rough sketch of how people in the field of science and also in some of the life sciences have been thinking about mechanistic explanation. Now, what about deep learning specifically? Well, as I mentioned at the outset, there is this emerging field, or at least I don't know if it's really emerging anymore in the kind of timeline of deep learning, which progresses so quickly. So certainly been around for a number of years, but it has crystallized around this label of mechanistic interpretability, which interestingly appeals to this notion of mechanism. And it's a bit of unfortunately, it doesn't have very clear boundaries. So there are a number of different technical terms of art that are used to refer to similar methods and similar concepts, but also sometimes the same terms are used to refer to different things. So it's a bit of a minefield. But I'll try to give a kind of holistic overview of that field. So generally, researchers interested in mechanistic interpretability, and starting with people like Chris Olah, operate with a kind of guiding metaphor, which is that we can treat black box, quote unquote, neural networks like compiled codes that could be reverse engineered. So that's the kind of software engineer guiding metaphor. I think it's a little misleading. I'll say more about that at the end, but I think it kind of over promises about what really is happening and is going on in this kind of endeavor. And I think the reality is more that we can hope to develop abstract causal models of mechanisms in artificial neural networks. So that's going to be one of my claims, is that that's a better way to think about the project of mechanistic interpretability. And importantly, these models are supposed to map onto what is often referred to as circuits or computational subgraphs of the network. Now, that's also a little tricky because the different projects of mechanistic interpretability represent the network of the computational graph of the network at different levels of granularity. So some papers will represent the computational graph of network as literally each neuron being a node, and each connection between neurons being an edge, while a lot of papers will kind of look at it at a higher level and isolate some clusters or more meaningful units in the architecture of the network that are not single neurons as the nodes of this computational graph. So that's the more common way to do it, and I think the more interesting way to do it. And so, for example, you can view a transformer model as a causal graph where we interpret attention heads and multi-layer perceptron as the nodes or the variables of the causal graph. So that's the common way to think about transformers in the mechanistic interpretability literature. And often that's done with time models that are simplified versions of transformers. That's what I'll take as an example here, just because it's helpful, but it doesn't have to be time models. If you do this, so here you have time model of a transformer that takes as input tokens. These are linguistic units, can be whole words, can be subwords, and then embeds them into vectors. I'll glance over some details like positional encodings. The important bit here is the let me see if I can use the laser. These attention heads, which are a very important component of the architecture of the transformer architecture, which perform some operations on the vectors for the tokens in the input and transform them in some ways. And so you have in the different layers of a transformer here, I'm just showing one layer. You have many such layers. In each layer, you have several attention heads that work in parallel on all of the input tokens, or at least all the tokens that precede the position at which they are attending, and they perform some manipulation of information, transformation of information. One of the interesting insights from the mechanistic interpretability literature is that we can think of this whole network as operating on this thing called the residual stream. And the residual stream is kind of a central communication channel where for each token position in the input, these attention heads are routing information and performing some transformation that then is going to be added back to the residual stream or to this central channel. So the idea is that you have these vectors that encode the tokens in input. They get transformed in some ways by these attention heads, and what that can be, what we can look at that as the attention heads are reading information from the residual stream or this central channel and writing back information onto it. Okay, so. And so in that sense, attention, or this attention mechanism, routes information selectively and dynamically in the network. So these attention heads that perform mostly linear operations that route information across tokens and across layers, or across token positions and across layers in the network. And they do this by projecting the original high-dimensional vector embeddings for the tokens into lower dimensional subspaces. So they take these embeddings as input and they transform them in some way, and they transform them by manipulating information in different subspaces of the main embedding space. So in the interest of time, and I think of complexity as well, I optionally had included a detailed walkthrough of a specific example, something called induction heads in a transformer. I will skip that because we don't have time for that. But I will focus on a more high level example of the output of mechanistic interpretability. So this is from a paper that is a good example, as good as any, of what mechanistic interpretability researchers end up with. And this particular paper looked at a specific phenomenon or behavior of language models, which is the identification of the indirect object of a sentence. So specifically, here in this kind of task, we have a sentence that involves an initial dependent clause, such as when John and Mary went to the store, comma, and that's followed by a main clause. John gave a drink to, and in that case, the indirect object is Mary, and the subject is John. And so the task for the network is to predict the final token, which is again going to be Mary, in the sentence, predicted to be the indirect object. And so what these researchers did, Wang and colleagues, is that they used the tools of mechanistic interpretability to figure out how that happens in the network, and specifically figure out how attention heads at different layers. You can think of the x-axis here as corresponding to the different layers. So the further you are to the right, the further you are to the final layer, to the output layer of the network. Attention heads routing information, as we've seen, in a way, in such a way as to implement computations that together can be looked at like a little algorithm that will tell the network that given that input, it should predict Mary at the end. And so to do that, I'm not going to go too much into detail because I was building on my previous explanation of induction heads, but and it's not really very relevant for the overall argument, but it's, you know, you have different attention heads that specialize in different roles, different functions. So some of them will identify that John precedes the verb went in the first clause, and then another will identify that John in the second clause is a duplicate of John in the first clause. This is part of a broader circuit that will, at the end, inhibit the prediction of John and promote the prediction of Mary as the final token. Because when Mary and John went to the store, John gave a drink to John, doesn't make sense given the construction of the sentence. Okay, so how do we end up with this thing, which is, again, what researchers in the field called a circuit, which is a computational subgraph of the network? Well, the tools that I use essentially fall under the umbrella of what's known in statistics as causal mediation analysis. And causal mediation analysis is a statistical tool that elucidates the process through which a particular cause, or in this case, a particular input, which we call the independent variable, influences a particular outcome, which is a dependent variable, and influences it via an intermediate variable, which is also known as the mediator. And so the idea is that to distinguish between the direct effect of the independent variable on the outcome and the indirect effect that operate through the mediator, we can do that by measuring a change in the output following some kind of counterfactual intervention on the intermediate variable or on the mediator. So that's the mediation analysis part. And so through this intervention, we can measure the degree to which inputs influence outputs directly, so that's the direct effect, or indirectly through the mediator, through the intermediate variable, is the indirect effect. So in the case that we're interested in, which is the case of neural networks, the mediator can be any modal components that we want to study. So for example, attention heads, or even neurons, if we want to have a causal graph at the final grain of analysis, but here it's attention heads. And we can perform multiple controlled interventions on these mediators to reveal their causal role in the model behavior. So suppose we represent the whole computational graph of the network as this kind of graph, like a DAG, and we have certain inputs that leads to a certain output when we perform a forward pass through the model. So that would be the target phenomenon that we're trying to explain. What we can do is we can have a corrupted run when we change the input such that it changes the output. So we change the input, for example, the input sentence to downgrade models to have as a prediction John instead of Mary. We then take when we do these forward passes in the first time with the initial run, we freeze the activations of the network, and then we can substitute. That's also called an interchange intervention or activation patching. We can patch the corrupted run with the value for a certain node from the initial run, and we can see whether that has what kind of influence, downstream influence that has on the output. And we can perform that iteratively with all the different nodes and edges of the graph. And so essentially, we want to see which kind of patching of the corrupted run will lead us to recovering the desired output. And that should tell us which subgraph is actually relevant to producing the particular output. And so the idea is that should give us, at the end, a mechanism that has different components organized in a certain way as to be producing the behavior of interest. Okay, so back to mechanistic explanation. I think intervention methods like activation patching can reveal which model components are causally implicated in producing a particular outcome. In that case, model components being things like attention heads, for example. And the circuits that we end up with show us how the model components and the activities, so for example, the attention heads and their routing of information, are organized into the relevant causal structure for the phenomenon of interest, such as indirect object identification. And of course, and I can't get too much to the details here, but there are additional sanity checks that are often, perhaps always required. You could have so-called interpretability illusions. There is some recent work on that that's really interesting, where you can be led astray by some versions of activation patching. But generally, I think the kind of international approach of mechanistic interpretability is sound as an approach to abstract causal modeling of deep neural networks. So I don't want to be too long, but I just want to say something about this notion of interpretability before I close. So I think there is a worry that lurks in the background of this whole mechanistic interpretability literature, which is this focus on human interpretability somehow problematic? And that's very striking if you read some of the key publications from people like Chris Olah. There's this intense focus on making everything interpretable by humans. Again, reverse engineering the algorithm of a neural network as you would with compiled code, such that you would end up with the source code. And so the worry here is that would that end up leading us astray by kind of promoting just those stories about mechanisms that just happen to fit what is interpretable to us? And going back again to this initial comments I made about the alien narrative, maybe some things that neural networks do are generally alien in the sense that they're beyond interpretability. I think that depends. I think it's an interesting question, but really the devil is in the details, and it depends specifically at what level of abstraction you're pitching your causal modeling. So rather than talking about interpretability, you could argue this is just semantics, but I like talking about intelligibility in the sense that what's really interesting about the causal model you end up with is that it's intelligible in the sense that it has fewer variables than the target, and it has fewer causal connections as well. Have fewer nodes and edges, and so it's a way for us to contemplate the entire causal structure of the target in a way that we couldn't even begin to hope for whole networks. And furthermore, each variable in the causal model should, in principle, have an intuitive interpretation if the level of causal abstraction of the model is right. So if you think of the indirect object identification circuit, we can look at these involuted intention heads, and we have a good intuitive interpretation of what these heads are doing, how they're writing information from one layer to the next. And so the goal of this causal modeling is to provide us with an understanding of how the system produces the phenomenon. And hopefully it should illuminate that causal story in a way that doesn't just leave us with a kind of inscrutable redescription of what the model is doing. And so, for example, if we take the canonical examples from the mechanistic interpretability literature, circuits show us how information is routed through layers of high attention heads, as I mentioned earlier. And in the ideal case, we could hope to translate the high-level causal model as an algorithm in pseudocode. That's what sometimes mechanistic interpretability researchers do, in line with this aspirational goal of reverse engineering neural networks. And I think we can do that actually pretty effectively for highly targeted phenomena and tasks like indirect object identification or various other specific phenomena that have been investigated with mechanistic interpretability. But the fact that we're focusing on these very highly targeted phenomena is very important here, because that gives us a leeway to perform these very surgical interventions where we can make a very minimal perturbation to the input and then swap out or patch the activations of the corrupted run to have a very precise end up with a very precise pruning of the causal graph until we get some kind of subgraph that seems to be specifically causally involved in producing the target phenomenon. And that becomes very quickly intractable if instead of focusing on highly targeted phenomena, you start focusing on much vaguer, broader phenomena where specifically when you're looking at end-to-end circuits from input to outputs. And then if you try to impose interpretability at all costs, you run an exponentially greater risk, I think, of being led astray to just those stories. And also, so there is this point about the kind of level of specificity of the phenomenon you're targeting. But I think also the fact that we're dealing with causal abstractions is key to the fact that the explanation we end up with provides us with understanding. That trying to understand deep neural networks at the level of individual neurons is tempting, and a lot of mechanistic interpretability researchers are moving in that direction. But I think that's, to put it harshly, probably hopeless or useless, because the value of the explanation we end up with is that abstraction. I put as an illustration here this earlier work on neurons in convolutional neural networks, like computer vision models, where some neurons you can try to see what kind of input would maximize their activations. You end up with images like this. Some of them are just not very interpretable. So that's a case where you have kind of cat features and car features, and that's more common than not in these networks. Now we could maybe get into that in the discussion. There's some work on polysemanticity and try to disentangle superposed features in neurons, but I think personally that the work on circuits that are pitched at a higher level of abstraction is more promising and interesting than trying to reverse engineer the activity of individual neurons. Okay, I've spoken for a long time, and I'm still feeling quite woozy, so I'll stop here. Thank you.
Thank you very much. I have to remind the people who came late that what Raphaël was struggling with, besides the subject matter, was it was 3 a.m. in Australia, that he has COVID and that he's highly medicated. So I really congratulate you for getting through it. Like, there will be questions, but I may as well kick it off with a simple one, a naive one. Yes, we all want to know causally how LLMs cause remarkably informative performance that they're capable of generating. So in other words, they do something and we want to know how they do it and why, what more than that, why, what it is that they're actually doing. And except for the secrets of OpenAI, we know what they're doing. Why that stuff generates what it is that they're doing. Now, when you were talking about intelligibility and interpretability, I was getting a little mixed up because sometimes it sounded like the interpretability of what comes out of an LLM or a DALI or whatever, versus the interpretability of what it is that the LLM is doing in order to produce that output. So the thing that you called reverse engineering of the code, which I'm not familiar with reverse engineering of the code. I'm not a computer scientist, and maybe this is a philosopher's term. But I feel that from everything that you said and everything that follows from what you said, a mystery of how on earth that stuff produces that output is not even touched. Can you tell me how it's meant to dispel the uncertainty about that?
Right. Thanks. Yeah. So the kind of intelligibility or interpretability I was talking about is about how the system is producing a certain output, how it's going from input to output, or sets of input, sets of output for a specific task, for example. Right. So the task could be identifying the indirect object of a sentence. It could be performing some kind of arithmetic operation, whatever specific targeted task you could throw at a neural network or at a language model, the kind of stuff you could have in a benchmark, for example. And so, yeah, the interpretability question is about how the network is doing that task.
But didn't you answer that question when you were talking, saying that, well, roughly speaking, if we take the entire net graph, etc., that's the answer to how it's doing that.
Well, that's where it's important to keep in mind the distinction between a descriptive model and an explanatory model, right? So if you're just really describing what say the piles of linear algebra that are occurring inside the network, or if you give the standard story about these are just next word predictors and so on, you're not really providing an explanation in the genuine sense we're interested in, right? So part of the benefit of a mechanistic explanation is that it enables us to have some kind of actual understanding of how you get from input to output. So it dispels the mystery, but also it enables us to intervene, to manipulate any component of the mechanism to control the system. So that's we have this kind of epistemic benefit and benefit in terms of control of the system. And we get neither of these from just reading out the linear algebraic operations that the raw network is performing. So I don't think it's really providing us with an explanation in a genuine and non-trivial sense of how the network goes from input to output.
Okay, sorry, I have to manage the people in this room as well. I'm going to pass it to your co-author in a second, but I just want to pursue a little bit further. I agree with you. There is a mystery that is not dispelled, for example, in the case of neuroscience. If you say, look, we know that the brain is doing it. This is what the brain is doing. Now tell me how it does it. But that mystery is not dispelled with the brain. And it's certainly not dispelled even with the brain if what you say is, okay, I'm going to remove part of this, or I'm going to stimulate part of this, and you'll see it's an intervention. It's going to change stuff that's happening. That's not a satisfying explanation either. Or with these networks, it's even truer that even if the kinds of things that you say we have not yet done, it's not clear to me from that. Perhaps something magic will happen when you say the words. But nothing from this stuff about when you can show that Mary, yeah, you know, what you said about the phrase about Mary, that's going to dispel the mystery for me. It's not that I think it's a terminal mystery. I think there is something to be explained, but I don't see how this approach is going to dispel it. And I'm going to let Dimitri take it over from there.
So just very briefly, the key part is that when you find a circuit for these techniques, then you interpret the circuit, right? And the interpretation ideally should be such that you could literally write the algorithm, write it down in, you know, the language of your choice, in Python or in pseudocode, that the circuit is implementing or approximating at least. So that's where you get this genuine explanatory purchase, because it's not that you just find out that, oh, like all these parts of the neural network are causally implied, but I have no idea what they're doing. Is that you see that they're causally implied, and you know how they're causally implicated. You know how they're causally implicated because you've identified how each component, in this case attention heads, is routing information to the network and what kind of information it's routing. So again, the idea is to try to reverse engineer the algorithm that supports a certain.
Thank you. I'll give your COVID a break. There are lots of questions coming. So Dimitri's first, and then we have say your name.
Véronique.
Véronique second, and then I see we have Alizi and Rob Goldstone. Go ahead, Dimitri.
Yeah, thanks a lot for this, Raphael. I mean, I'm not a co-author in this paper, but I agree with everything, so I could very well have been. But so I have a question about things more towards the end that you mentioned about, you know, understandability or intelligibility, and, you know, how this ends up being somewhat, you know, dependent on the, you know, humans in the end, what is understandable to humans and so on. And I was wondering, because one risk, I suppose, is that we end up, not necessarily with just those stories, but with things that are very approximate, because we try to apply concepts that come, you know, from cognitive psychology or from comparative psychology to things that might not be, you know, good targets for those kinds of concept applications. So I was wondering, you know, whether you think there can be ways in which we see the intelligibility or understanding of those sorts of explanations that may not involve us applying concepts that we already have, but perhaps, you know, coming up with new ones that may be better suited for these systems.
Yeah, thanks. That's a fantastic question, and there are so many different directions we could take that into. I just mentioned, so there is work. If you think of the cases where the computational graph is literally, spanning the whole network at the level of individual neurons, like people like Chrysola have been trying to do. There's this work that tries to automate the interpretation of features supposedly encoded by individual neurons. There's this recent work that used GPT-4 to try to interpret the neurons of a small model. I'm not very optimistic about that line of work. In fact, there is a recent paper by Chris Potts and others from Stanford showing that these particular results from OpenAI was mostly bogus. So that would have been one case where you might hope, oh, well, actually we can automate this work of finding out which concepts are encoded by neurons, even if they might be weird. But at the end of the day, what the model is doing is still providing a natural language description for the features supposedly encoded by the neurons, and therefore they're still human interpretable because they use natural language. But taking your question more broadly, trying to remember now where I wanted to take this in my
For your drug.
I had several. So there is another thing that relates to your question, which is there's this recent paper on interpretability illusions that's quite interesting. It's showing that sometimes you can have, you use the standard intervention method on a certain distribution for a task, and you have a neat circuit that you find, and you can interpret what the different attention heads are doing, and it's all looking great. And then actually, when you look at you test your model and your circuit on inputs that are slightly out of distribution, and then distribution shift, you realize that your attention heads are doing completely different things. So that's something that seems to be happening quite a bit more than people anticipated, and might be related to various complications about this idea of superposition and so on, but it's really messy. And so I think this kind of interpretability illusion is not unlikely to happen, and that's a further concern about trying to superimpose a very neatly kind of obvious interpretation of what's happening. But the final thing I would say with respect to your point about concepts from psychology, maybe everyday psychology, I don't see these concepts generally playing a very prominent role in the kinds of explanation provided by mechanistic interpretability work, which I think is a feature. So if you look at, the indirect object identification circuits or induction head circuits or various other circuits, one benefit is that they really avoid sidestep all of this psychological terminology, because they're really, again, trying to provide a very low-level algorithm for how information is routed. And of course, then that opens another question, which is, I think, one you're exploring in your own work as well, which is how you would bridge these low-level algorithmic explanations with the high-level behavior of the system. And then we need some kind of equivalent to cognitive functions to try to bridge these two. But I do think it's a feature of the mechanistic interpretability endeavor that it's starting from these really basic building blocks that very much look like the kinds of variables that a basic computer program would work with. And hopefully we can gradually build that up to find a bridge between that and how we might describe the high-level behavior of the network as doing things like reasoning or planning, etc.
I have to intervene there because we're not going to get to the other questions if we give such long answers.
I'm sorry. Yeah.
Relax. The next question is Véronique.
Yeah, I have a question about the central communication when you give a token.
Poser la question en français, il est francophone.
Correct. Yeah. So when the token comes, the central communication, And with the example of Mary and John, if we add someone else to going to the coffee, so for example, Louis, Mary, and John, well, the system will be available, will be capable of identify Mary as the wife of John, for example. So let's change the sentence. Louis, Mary, and John are going to the coffee shop, and John buy a coffee for his wife, and the system has to say Mary because it's the only woman. So because it's a central communication, do you think that the system will be able to give this answer?
So there are two questions here: whether the model will be able to give this answer, and how the model would be able to do that. I mean, these models are pretty good at this sort of thing. So you know, they can do pronoun resolution, like of ambiguous pronouns, quite well. They can you know, pick up even on various pragmatic cues that we use in language to resolve ambiguities in discourse. So I'm not, I would, you know, I think it wouldn't be that hard, I think, for the models to do. It's just that in that particular case, it would become a different task from the task that I was talking about in the indirect object identification example, which is a simpler task. But there has been mechanistic interpretability work, I believe, on resolution of the reference of pronouns. So like finding a circuit that resolves who a pronoun is referring to, something like that. So yeah, you could apply, I think, the same kind of general procedure in that case.
Okay, can I ask you to unshare? I think you're still sharing.
Yes.
Okay. Unfortunately, we lost Rob Goldstone, but he'll be back. He'll be giving a talk on in this series as well. Allez-y, it's your turn, and then Steve Hansen has a question.
Je peux vous en français, pas de problème.
Allez-y, vas-y.
Salut Raphaël, merci.
On s'entend pas.
Ma question est la suivante. Et comment les explications mécanistes de l'apprentissage profond, en particulier dans le contexte des modèles de langage LLM, se différencient-elles des explications mécanistes traditionnelles dans les sciences de la vie? Alors, y a-t-il
You
des
understand,
défis ou des
Raphaël?
avantages?
Loud enough?
Yeah.
C'est correct?
Okay.
Y a-t-il des défis ou des avantages uniques inhérents à l'application de ces explications aux réseaux neuronaux artificiels, par exemple?
Right. So the question for those who don't speak French is how are the kinds of mixed fantasy explanation provided in the case of deep neural networks and language models differ from the kinds of mechanistic explanations that might be provided in the life sciences? And I think there are, you know, if you squint hard enough, they're not that different from the kind of explanation that people aspire to in cognitive neuroscience, cognitive computational neuroscience. But the key difference, of course, is that the kinds of intervention methods that are available to us in the case of artificial neural networks are, you know, in a sense, vastly superior to anything we can do with real brains, because we have a full knowledge of all the states of all the activations of the network, and we can manipulate any of them as we wish. And that enables us to end up with mechanistic explanations that are already, even though it's still a very hard project, much more satisfactory, I think, than the kinds of mechanistic explanation that neuroscience, which arguably is still a very young field, is achieving with, at least with human brains. Obviously, like we can perform fairly sophisticated interventions, specifically in very simple animal models like C. elegans. But yeah, I think that's one difference, is that you can hope to achieve in principle much more complete explanations, whereas in other life sciences, generally philosophers of science, talk about mechanism sketches, just kind of incomplete sketches of mechanisms.
Okay, next question from Steve Hansen. Turn on your sound.
How about that? Can you hear me?
That's good. That's good. Can you hear Raphael?
Hi. Yeah, I enjoyed the talk. And I generally agree with some of your points, but the problem is the transformers are both trivial, that is, behaviorally, what they're asked to do is not much more than I ask my cat to do every day, predict what's about to happen. And internally, the structures are also unremarkable. I think you said a lot about attention heads, but attention heads, if you actually, and I've written a few GPT programs myself, are nothing more than autoregressive functions. So that is, they can create circuits, but the circuits aren't any, if you put up a Wang, I think. Now, Wang actually introduced logical circuits into pre-trained GPTs. That did not evolve. So there's other speakers in the seminar and other people out there who have tried to analyze internally what the attention heads are doing. And it's very unclear. There does seem to be some logical circuits and some simple kinds of positional structure that's there, but it's very obscure. So it begs the question in terms of especially either I think your argument says, let's simplify and try to make sense. It seems to me that that's a hopeless approach because the scaling of this is what's critical. The fact that you go from 9 billion to 900 billion, and then a green orb drops in your backyard and it starts talking. This is what's happened to us, and we don't understand it. And any kind of rationalization of this at this time, I think, is a disservice to trying to figure out what's going on. I think there's a lot of computer scientists. OpenAI is filled with them. Google, I'm sure, is doing the same thing now, and they've tried. There's lots of tricks here. And if you look carefully at a GPT program, you go through it, it's a hack. It's a hack. They have numbers in it like, oh, let's put 10,000 here because that kind of worked the last time we used it. This is totally a hack. And the actual outcome, the way it appeared, is an accident. No one knows how to do this again except to copy what happened before. The structures of these things will remain obscure for a very long time. So the question, I think, for a philosopher is how to frame this in a way to make sense so that people can, in fact, approach something that looks like a causal explanation. I just, I do a lot of graph modeling too. I don't see, I mean, if I build a 900 billion connective graph model, I've got worse than I started with, right? It makes no more sense than looking at the structure of this. So I'll stop there.
Thanks. Yeah, I mean, look, I agree that the architecture, the transformer architecture, is not very complicated. It's in fact deceptively simple if you look at the architecture itself, right? It's like it's there are some tweaks to the architecture people have made, changing positional encodings and doing other things differently, having different kind of attention, but the basic building blocks are very simple. The attention mechanism is very simple with these key query value vectors, and MLPs are just simple, fully connected networks. But the key point that I want to make initially in my talk is that just looking at the architecture is not going to tell you much about what these systems can and can't do, right? You need to look at the trained networks. And what's interesting about a trained network is that there's a lot of structure that emerges through training. Looking at untrained attention heads just at the code for the architecture of the model is not going to tell you anything about these structures. And so during the course of training, attention heads will specialize into modeling specific kinds of dependencies or working together across different layers by composing into circuits. And that is the thing that people in the mechanistic interpretability field are trying to understand. And I'm not saying it's easy, and I agree with you that the scalability is a problem. But actually, the recent trend over the past year has been to develop some automated techniques for scalable mechanistic interpretability. And so nowadays, people have done work that has been scaled to models as big as Llama 2, which is 70 billion parameters, or Chinchilla from DeepMind, with great success. So they've been able to decode some very sophisticated circuits with these automated techniques that essentially involve automating the process of interchange intervention with some tweaks to optimize it, because it becomes intractable if you do it in the traditional way. So I don't know. Look, as I said at the end, I'm not very optimistic that we'll be able to have a full end-to-end kind of mechanistic explanation for complex behavior of a model like GPT-4. However, if we could manage to at least reverse engineer, as these people would put it, some building blocks of the capacities these models have in terms of circuits for certain forms of variable manipulation, variable binding that are crucial to reasoning, for example, that would already be of huge progress in terms of our understanding of how these models do what they do.
Are you satisfied?
Did you just ask me a question?
I just asked you whether you're satisfied.
Well, no, not really. I mean, I see, at some level, your conclusion sort of leaves us at some kind of perverse behaviorism. We can, ask the same questions, we can get it to jump through hoops and so on and so forth. But the deeper understanding of this, so it's not like someone went through some principles here, sort of like what we thought in the 70s. There would be some kind of principles of AI, and it would sort of move things in this direction. Instead, we just saw this pop, and this happened. And now everyone is caught kind of with the tide out, and we have no idea what happened. And recapitulating this in various philosophical ways, I don't think is helpful unless we have more circuit structure that actually emerges and we understand it. Then all of your initial arguments make sense, but then it might be better to do some kind of causal graph modeling within the attention heads directly. So there's a lot of empirical work here, not logical work, I think.
To meet,
I will really stop there because I have to go meet with somebody important.
Okay, I just want to, before you go, and there's also Anna Maria who has a question, but Dimitri suggested that the kind of work by Pavlik that you thought you quite well of was doing the kind of thing that Raphael had in mind. Do you agree?
Yeah, that's right. I mean, she was doing hard analysis of circuit work and basically looking at the emergent structures, understanding they're there, but they're so complicated at some level they can't be there. And this is what the paradox is. How do we get this complexity out of nothing? And since we haven't built anything in, it really, Jeff Hinton basically told me last year, he says, aha, okay, this is what I sort of expected. I said, what are you talking about? You can't expect it. This is exactly what we would have hoped, but no one expected this. So I literally have to go meet with somebody.
Okay, you're excused. Anna Maria, go ahead.
Nice seeing you.
Anna Maria.
I just want to say first that I'm agreeing with the previous comments that we just heard. And I want to point out to the fact that this model, or trying to interpret a system mechanistically, might have its merits. However, it does not take into consideration the notion of explanation in science, right? A scientific theory or is explanatory in terms as with respect to simplicity and other aspect that it accounts for the object of inquiry. Then if you're talking about natural language, there's various theories of what are natural language, and one of the proeminent theory is the idea that language is something that is biological, and it came about sometime in recent historical past, considering all the time of the universe, for example, and should be simple. And what are these properties? It's, structure dependency, not heads, heads and their dependent, and semantic compositionality. Now, there are semantic theories of semantic compositionality that I don't see in ChatGPT. I don't see structure dependency in terms of oriented graphs, as it should be, and not dependency graph, as generally there's a trend that tries to bring this dependency graph later on in the transformer at the higher level, but then it's too late because you don't have a system that analyzes linguistic expression, has structures with elements included in the structure which are not overt, the one left by displacement, for example. So fundamentally, thinking about natural language as sequences of words is flawed from this perspective. And thinking of taking aside the problem of how we acquire language, of course, this is an artificial system, it's not a human being, but how mechanistic models would approach this, at the end, there is little hope from my perspective that system like GPT, whatever number, achieve some, scientific interests, not to say also, technological interests. So I'm surprised that all the work that has been done in technology and its science in the 60s or the 70s, the automata model and so on, is completely gone from the sight of a researcher now.
Anna Maria, if you want to have an answer during this time that's left, I think you should cut the question.
So this is a comment, and I would like to know what is your view on this, what I just said, and maybe it's too long of a you can reply, I disagree, and I will be satisfied.
Okay, fine. The question is posed. Now go ahead, Raphaël.
All right. Well, thanks, Dot. Yeah, so that takes us a little bit further away from, I think, the specific topic of my talk, but it's something I'm very interested in. So I actually have a paper on that very kind of question about, linguistic nativism and language acquisition and how that relates to language models, and specifically what is the status of language models as models of language. So that particular, it's a chapter for an upcoming handbook, but it will be pre-printed soon. But there is a section in that paper with Cameron Buckner that I mentioned, that I just put in the chat, that gives the very rough gist of the argument. And I do think that, first of all, there is a lot of evidence that language models encode a considerable amount of information about syntactic parse tree and generally the hierarchical structure of language. There are a lot of experiments, including interventional experiments, that demonstrably show that they not only encode but make use of information about complex syntactic structures to produce their outputs. Now, as far as the so that's the question about syntactic competence. But as far as the question about their plausibility as perhaps model of language acquisition or model learners, and whether they might call into question nativist accounts of language, like in the Chomsky tradition, it's tricky because there are different versions of the so-called poverty of the stimulus argument. We don't have to get into that now. I think they certainly call into question the strong in principle claim stemming from Gall's theorem about the idea that there is no amount of stimulus that could lead a statistical model to learn just from exposure to linguistic data, the structure of syntax. Now there is a question about whether they're really calling into question the more subtle developmental claim about the poverty of the stimulus, as in children can make this constrained generalization from poor, impoverished stimulus to certain syntactic structures. But I think there is recent evidence even on that starting to tentatively maybe challenge some of these claims from language models that have been trained from much fewer, like a much smaller corpora of child-directed speech to try to reproduce as closely as possible the learning environment of children. So anyway, if you're interested in this, I give a very long answer in that paper that's forthcoming. But yeah, I'm not sure you will agree with the answer or like it, but that's my view on it.
It's all right. It's supposed to be science, so there's no emotion there, right? So it doesn't matter if I like it or not. But there's a lot of paper I can send you and books, and we could talk further. Okay.
Sounds good. Yeah.
I'm finished.
We run out of time. We run
Yes.
out of time. So all I can tell you is that the next speaker, if you thought that there was controversy now, the next speaker, Ben Goertzel, will be controversy up to a higher level of magnitude. And I invite you for next week's presentation. There's a little bit of uncertainty about the one right after that, because whereas Raphaël had, I hope, a very brief COVID, the speaker after Ben Goertzel has long COVID, and it might be that he won't be able to come until the very end of this series. But come back next week for Ben Goertzel, and we'll know what the health report is for the rest of our speakers. Thank you ever so much, Raphaël. And with that, I'm going to close this recording, and I'd like